we will just take a quick recap of what we studied in the previous class. The last class we essentially delved into a celebrated experiment which is known as Young's double slit experiment, that is regarded as one of the all-time 10 best, most beautiful experiments that have helped perceiving the design of nature. Let's go a little behind in history to understand the importance of this work. Late 17th century, in 1690, to be more specific, a Dutch physicist, Huygens, suggested that light travels as a wave, and which is known as popular as wave theory of light. However, within just few decades, this wave theory was contested by Isaac Newton, who proposed instead corpuscular theory of light, where he assumed light to be comprising of a bunch of stream of particles. Einstein's authority was so pronounced in the scientific world that nobody could challenge this corpuscular theory of light, even for almost 3/4 of a century after his death, until Young performed this famed experiment. The experimental system that he used to do this experiment was fairly simple. He used a, we have studied all this, so I'm just giving you a brief summary. He used an opaque barrier into which two slits were etched. I'm showing you in 2 dimensions. So actually, these two slits would look like this. And he placed source symmetrically in front of this. Means this was a point source, and this source is equidistant from this to slit. And behind this barrier, opaque barrier, he placed a viewing screen. Now, if light were to travel, light were to behave as particles, then it would obviously leak through this to slit and reach these two regions of the screen, creating bright spot or bright stripes. And light would not be able to reach any other place on this viewing screen if light were to behave as particle. But in the experiment, Young found that at the center of the screen, which was again equidistant from these two slits, there was a bright region, and light, this presence of this opaque barrier would forbid any light reaching this region. And not only that, there was alternate bright and dark zone that was observed on the view screen. So these were bright, and in between dark. So obviously, this observation could not be explained by considering this corpuscular theory which was proposed by Newton. But this observation can be explained if light travels as a wave. So for this, let us go to this illustration, which is wave theory based interpretation of the formation of alternate bright and dark regions viewing screen. So you see, this is our screen, and this is the source, and we consider the wavefronts emanating from this source and moving forward. These are the alternate crest troughs. Now, as these two slits are equidistant from the source, therefore, a ray of light originating from the same wavefront would simultaneously strike it, because this is equidistant from it. So, the light will reach at the same time from the source. If it has started at a particular time, it will reach the two slits simultaneously. Now, according to Huygens' wave theory, these two slits now perform as two secondary sources and would emit their own sub-wavelets in unison simultaneously. So these are the sub-wavelets emitted by the upper slit, and these are alternate crest and trough. Blue color means these wavelets have been originated from the upper slit, and the red wavelets are originated from the lower slit. Now we know that at this point there has been a bright region, the viewing screen. Now see, this is equidistant from the two slits. So the two waves which will reach this point, they will be always in phase. For instance, you see on this line, all the points are equidistant from these two slits. And therefore, on this point, the crest of one slit meets with the crest of the other slit, or trough one slit meet with the trough of other slit. That means the waves always meet on this line, which is equidistant from these two slits in phase. That means they will interfere and reinforce each other. The intensity will increase at this point, and light would indeed reach which particle approach of light, corpuscular approach, it could not explain. And then let us turn our attention to the dark zone on the screen. Now, on this line, you would see the crest of one slit originating from one slit meets with the trough of the other slit. So that means the crest of one here lines up with the trough of the other, and vice versa, trough of the other and crest of. So that means they will annihilate each other. There will not be any energy at this region. There will be conservation of energy, of course. So the energy, the dark, actually appears as the energy, the intensity, the bright. Now you see, this is the wave theory based interpretation of Young's double slit experiment. So this actually re-established the wave theory conclusively and allowed the flow of knowledge ever since. Now, there is a very important conclusion that we can draw from this. That is, if we can express some analytical relation with regard to formation of dark and bright regions on the screen. For this, we consider this, take another closer look, the Young's double slit experiment. Now let us consider first this bright fringe. Now see, the two rays which have originated from the two slits, like this ray and this ray. Obviously, these being equidistant from the two slits, they have traveled equal distance. Therefore, the path difference of these two rays, as they starting from the slits, they reach this point, is zero. They have traveled same path. Therefore, we can say that when the path difference of these two rays that are interfering at the screen is 0, then you have a bright region of intensity. Similarly, if we turn our attention to the next bright fringe below the central bright region, here as you can clearly see, the ray which is originating from the upper slit has traveled a longer distance compared to the ray which has started its journey from the lower slit. And because they have again interfered and created bright region, that means these two waves, of course, they are in phase. That's why bright region has been formed. But what is the path difference between them? This has traveled a longer distance. Because they are in phase again, therefore, this has traveled a distance which is just one wavelength more than the distance traveled by this ray. So this distance, if this were x, this will be x plus lambda. Only then they will interfere constructively. They will reinforce. Because the wavelength is that 2 points on the wave, they are in phase. So if you move it by one wavelength, it will be still in phase. I hope you are able to appreciate this point. So then, at this point, the path difference of these two rays, which have interfered and created and produced a bright region of intensity, the path difference is lambda. So you have it. Similarly, if you come to the next bright fringe, here it is easy to show that this ray, which started its journey from this slit, has traveled even longer distance compared to this. And because they're still in phase, produced another bright region of intensity. So the path difference here must be 2 lambda, so that they're again in phase, the two waves. One has traveled 2 lambda distance, twice of wavelength distance, more than that. Now, similarly, if you consider the region which has been formed above the central light range, the same logic again applies, except that the ray which starts from the lower slit now travels a distance which is more than the ray which travels from the upper slit. Nevertheless, there's separation, path difference once again lambda. Similarly, the next one, the path difference will be 2 lambda, which will be again. So then, what we have seen? We have seen that the path difference is lambda, lambda, 2 lambda, 3 lambda, 4 lambda, and so on. Then you have a bright zone. Now let us turn our attention to the dark zone. So this is the first dark zone below the central bright. Here, this wave has traveled, of course, a longer distance than this wave. And because they are out of phase, because they have interfered, they have annihilated, the intensity is annihilated of the two waves. So that means they're out of phase. When they will be out of phase? When one wave has traveled a distance which is half of wavelength more than the other. Only then they will be out of phase. I think you are able to appreciate this point. So then, for this, the path difference is lambda by 2 and you have dark zone. Both above and below this central. Next one, the path difference will be 3 lambda by 2. Lambda plus lambda. So 2x will be again out. So then we can say that if the path difference is lambda by 2, 3 lambda by 2, 5 lambda by 2, so on, then we have dark fringe. So this lambda, you see, these are all odd multiple of lambda. Similarly, you can express lambda as 2 into lambda. 2 lambda you can express as 4 into lambda. This you can express as 6 into lambda, 8 into lambda. So we can say that whenever the path difference is even multiple of lambda by 2, it is going to be a bright fringe. The two waves will interfere and make a bright fringe. And when the path difference is all odd multiple of 2, 1, 3, 5, 7, etc., it will be done. So we can actually express this analytically. We can say that if path difference is 2n lambda by 2, then there will be bright fringe. So if you have n equal to g, n is an integer 0, 1, 2, 3, the path difference is 0, lambda, 2 lambda, 3 lambda, and so on. And if path difference is 2n plus 1 into lambda by 2, you will have dark fringe. That means it will be lambda by 2, 3 lambda by 2, 5 lambda by 2. N is an integer. So now if you plot the intensity as a function of this path difference, then what you would see? You would see that suppose we start from here, we count our path difference from here. So this is 0. This will be lambda by 2 path difference. Huh? This will be lambda. This will be 3 lambda by 2. Lambda by 2. So when the path difference is 0, intensity is maximum. It is the brightest spot. And when path difference is lambda by 2, the intensity is 0, complete annihilation. 0 annihilation, that is complete reinforcement, and here complete annihilation, 0 reinforcement. But what happens for path difference lying in between? The fringe intensity will vary from 0 to maximum. So then you see, by manipulating the path difference between the two interfering waves, the intensity of light upon their superposition can be varied in a controlled manner. If you can vary the path difference, the intensity of the interfering waves after the waves interferes, the value can be manipulated by manipulating the path difference. So this is a very important conclusion. This can be exploited in fabricating the partially transmitting mirrors, for which is prerequisite for the making of a laser. You already know this. Just touch upon. You know that in case of a laser, just refreshing your memory, you have a inverted medium, that is a medium in which medium in which you have inverted population, and you place this between two cavity, which basically two mirrors parallel. And as it is an inverted medium, the photons which will originate from spontaneous emission, some of them which travels along the axis will continue to oscillate back and forth, and as a result of it will exploit stimulated emission because there is an inversion, and the light intensity will build up inside the canopy. However, light intensity will be built up in the canopy, but there must be some way to couple some of it out as useful loss, which will form your laser beam. So we know that one of the mirror must be a partially transparent, which couples out part of the light from inside the cavity, forming that is usefulness that forms the laser beam. Now you see, it is not that a particular partially transparent mirror will suffice for all the lasers. Different lasers, and even same laser, depending on their operating condition, may require partial transmitting mirror of variety of transmission. So how do there is special optics, special mirror? How do you fabricate such mirror? Well, as I said, you can exploit, you can take advantage of this conclusion, and you can apply that knowledge to fabricate such mirror. Let us go a little deeper. You see, we know that suppose there is a medium which we call medium 1, there is another medium which is, and this is interface 1, and this is the second interface. This is again. Now we know that when light shines onto it, a part of the light is reflected back into the incident medium, and remaining is actually travels into the second medium, of course, after exhibiting a bending, which is called refraction. Now, obviously, the question that can be asked here is, what fraction of this incident light is reflected into the second medium, and how this fraction of refraction depends on the refractive index of the two media and the angle of incidence. Suppose that these are the refractive index of mu2, and this is mu1. Well, I did not want to be here. It is the same medium 2, medium 1, medium 2. So medium 1 means, or refractive index is 1, medium 2, it's 2. Fresnel, French physicist, was the first to derive an analytical expression of where he expressed the fraction of light that will be reflected from such an interface as a function of the refractive index of the two media and the angle of incidence. Now, without going into detail of that, let us consider special case where light shines normally, so angle of incidence is 0. Now, if we assume that R is the reflective part of it in percentage, then from Fresnel formula, it would follow that for normal incidence of light, the fraction that will be reflected in percentage is, if this is mu1, this is mu2, it is mu1 minus mu2 divided by mu1 plus mu2 whole square. So if we into 100%, if we take, now for a laser, often glass is used as the material of the mirror. That is because glass offers wide transmission window, right from near infrared through visible into ultraviolet and even vacuum ultraviolet. So a wide range of wavelength light, so glass has full transmission, and that is why it is preferred as the substrate material of most of the optics that is used for the operation of laser. So we consider this medium to be glass. In glass, let us assume refractive index is 1. And let us assume this medium is air. That's what actually happens in reality. So if we plug in these values, then it will be 0.5 square divided by 2.5 square into 100%. So this will become 1 by 25 into 100%. So 4% of light, whatever is incident, 4% of that is going to be reflected from this interface. So remaining, that is 96% getting, which again needs this second interface. This is again glass and air. So again same formula will be applied, same mu1, mu2, and 4% of this 96% will again be reflected. And it will again strike this interface. And from here, only a very tiny portion, 4% of this will be too small. So we can assume, if we neglect this 96%, if we consider it's full 100%, then roughly we can say that nearly 8%, 4% and 4%, 8% of the light will be reflected, taking into account the reflection from both the interface. So that means nearly 92% of the light incident on it will be transmitted. So then finally what we have, you may now think that, okay, we will have a glass plate and you have your laser. Laser means that active medium, and you have one total reflective mirror. And you may say, okay, well, this is our partially transmitting mirror, because it allows 8% of the light that would fall from this active region of the laser into this, 8% will be reflected and 92% will be transmitted. So you might as well say, well, this will serve as the transmitting window, because 92% of the light that has been stored will come out as useful loss. It will form the laser beam, and it is offering a reflection of 8%, which will oscillate back and forth. So as you see, 8% will be reflected and 92% is transmitted. So you might feel, so what is the problem? This can perform as a transmitting mirror of the laser, but with so much of loss, you would most probably would not be able to make the oscillation sustain inside the laser. It will die out. Well, I will end here today and begin from this point the next class and see why this will not work and why it is important that we have a way to fabricate transmitting or partially transmitting mirrors for laser of varying transmission range.